We'll be deriving the power equations in a three-phase system today. The average power, the instantaneous power, real power, reactive power, and the apparent power of a three-phase system. Now it will be slightly different from a single-phase AC system, and we'll see what those differences will be. Uh, so to calculate, first of all, we'll start with the calculation of instantaneous power, as we did in case of a single-phase system. So instantaneous power is actually the power measured at any particular time t. So Pt will be equal to Vt It is the equation of instantaneous power. Now here what is Vt and It? Now we actually have three different voltages and three different currents in a three-phase system. So we'll be representing we have defined VA as VP angle 0 degrees. Now, since we are talking about instantaneous power, so we have to actually represent it in a time domain. So VAT will be equal to VP cos of omega t in the time domain. VP was the RMS value of uh, this system. Fine. So, but we need to find out when we represent in the time domain, instead of having the RMS value, we have the peak value, that's actually Vm cos of omega t. Now we know the relationship between RMS value and the peak value. The peak value is root 2 times the RMS value. So therefore it is getting multiplied by root 2, where Vp is actually, you can write this here, is the RMS value. Simply Va is Vm cos of omega t. Now instead of writing Vm, I am writing root 2 times Vp cos of omega t, where Vp here represents the RMS value of this voltage. And in a similar fashion, Vb will be root 2 Vp cos of omega t minus 120 degrees, and Vct will be equal to root 2 Vp cos of omega t plus 120 degrees. So this is like sinusoidal representation or the time domain representation of these three voltages. Now in each phase there will be current will also be flowing in each phase. So we have to find out, we'll be having the values of high AT, high BT and high CT. Uh, Again, if we take IP as an RMS value, therefore this will be root 2 times IP cos of omega t, and let us assume there is any phase difference between VA and IT, and that phase difference is shown here by the sign theta. So theta is actually the phase difference between VA and IA, and therefore IB will be root 2 IP cos of omega t minus 120 degrees minus theta, and ICT will be root 2 IP cos of omega t plus 120 degrees minus theta. So in each phase, VA and IA will be having a phase difference of theta, VB and IB will be having a phase difference of theta, and VC and IC, it will be having a phase difference of theta. We are assuming that IA, IB and IC is actually lagging behind in all of these three. Okay, so we have defined the three-phase voltage and the three-phase currents in their sinusoidal representation, and we want to find out the instantaneous power. Now in each phase, therefore we can now define the instantaneous power as, say for example, we'll write PAT will be equal to VAT into IAT. Similarly, PBT will be equal to VBT into IBT, and PCT will be equal to VCT into ICT. Now the total instantaneous power therefore will be total instantaneous power yes, sorry for that delay. So total instantaneous power in each phase, the power will be given by simply the product of voltage and current in that particular phase, PA, PB and PC. Now, total instantaneous power therefore will be equal to P equal to PA plus PB plus PC. So that is actually equal to VAT IAT plus VBT IBT plus VCT ICT. Now substituting the values of VA, VB, VC, IIB, IC. This was root 2 VP cos of omega t into root 2 IP cos of omega t minus theta plus root 2 VP cos of omega t minus 120 degrees into root 2 IP cos of omega t minus 120 minus theta plus root 2 Vp cos omega t plus 240 degrees into root 2 Ip cos omega t plus not 1 240 120 minus theta. So these are the three phase voltage and phase currents. This is the total instantaneous power. Now you can take root 2 into root 2 is 2 VPIP. 2 VPIP will be common. Inside you will be left with cos of omega t into cos of omega t minus theta plus cos of omega t minus 120 into cos of omega t minus 120 minus theta plus cos of omega t plus 120 cos of omega t plus 120 minus theta. We can now apply the cos A cos B formula, and if you solve this, you'll simply be left with 3 Vp 3 Vp IB. ठीक है. Cos A cos B, we can substitute the formula for cos A cos B equal to half of cos A plus B minus plus cos of A minus B. After substitution, you'll find out that you will simply all those terms will actually cancel out. You'll simply be left with the term that is 3 VPIP cos theta. ठीक है, cos theta भी रहेगा. So this is now the instantaneous power in a three-phase AC system. If you remember the instantaneous power formula for a single phase AC system, it was not, this is a constant term, fine. So if theta will be having any phase, if theta is say for example 30 degrees, Vp and Ip will also be having some values. So this is a constant term. It is not changing with respect to theta. But in case of a single phase system, the instantaneous power is a time varying quantity. It is still dependent upon time, and at each and every time you'll be having a different value of instantaneous power. But you can see now in case of a three phase system, the instantaneous power is constant, and this is one more advantage of a three phase AC system, that the instantaneous power in a balanced three-phase system is constant and does not change with time, unlike the single-phase AC system. This is the total instantaneous power, or you can now also say this is the total real power of the system. Now, if you want to find out the power per phase, you can simply divide by 3 because there are 3 phases. 3 Vp Ip cos theta divided by 3. So you'll be having Vp Ip cos theta. So Vp Ip cos theta is the power per phase, the instantaneous power per phase, whereas the total instantaneous power is 3 Vp Ip cos theta. You have to only note here that Vp Ip, it's not the maximum value of voltage or current, it is the RMS value of voltage and current. So if real power is Vp Ip cos theta, in a similar manner, this is real power, total real power, and this is real power per phase. Per phase, it is simply Vp Ip cos theta. This is the same formula that we have actually found out for a single phase system. There also we had discussed that power, real power is equal to Vp Ip cos theta, fine, where Vp and Ip are the RMS values. And but this actually, the only difference here is that this is per phase. The total real power will be thrice that. In a similar manner, reactive power Q will be, it is only the only difference between real power and reactive power is that one is a cosine term, another one is a sine term. Q will be equal to 3 Vp Ip sine theta. Q per phase will be Vp Ip sine theta, and the apparent power S will be 3 Vp Ip. There is no cosine or sine term here. Per phase it will be S per phase will be simply Vp into Ip. Fine. So this is reactive power per phase. This is apparent power per phase, and this is your real power per phase. And these are your values for total real power, reactive power, and apparent power. The units of which are watt, var, and Va, volt ampere. Fine. Uh, तो वहाँ पे VP IP cos theta था, यहाँ पे अब खाली thrice हो जाएगा because of 3 phases. That is the only difference between power flowing in a single phase system and power flowing in a 3-phase AC system. Also, that your instantaneous power here is constant. It is not varying quantity like that, like like we saw in case of a single phase system. The instantaneous power was varying in nature. Now with these, you have to actually remember these formulas. With these formulas in mind, you can now actually we can do some numericals on this. One more thing you have to keep in mind, these are RMS phase voltage. Now if you are given, instead of phase voltage, you have been given a line voltage, you need to also know which sort of connection it is, whether it's a star connection or a delta connection or something like that. Now in either, so if it is a star star or a star or delta delta connection, you know that either of these two terms, Vp or Ip, is going to be root 3 times the line voltage. Fine. So therefore, if we were given line voltage quantities, S would change to root 3 VL IL. Similarly, Q would change to root 3 VL IL sine theta, and real power would change to root 3 VL IL cos theta. Fine. Instead of having phase voltage, if you have the value of line voltage available to you, since Vp is VL divided by root 3 for a star connection, or for a delta connection IP is uh, IL divided by root 3. उस केस में VP और VL same होंगे. In case of a star connection, IP and IL will be same. So either of the two quantities, or it may be voltage or it may be current, will be divided by root 3. So 3 divided by root 3. तो आपका root 3 times हो जाएगा for either star connection or for a delta connection. It doesn't matter. So if we have been given the quantities in line voltage instead of phase voltage. So we have three phase voltage connected in a star fashion, 110 angle 0 degrees, 110 angle minus 120 degrees, 110 angle 120 degrees, and it is connected to a star shaped star connected load. You have a three phase voltage source, it's connected to a star connected load. The star connected load, this is 10 plus 8j, this is 10 plus 8j, 10 plus 8j, and your line impedance is 5 minus j2, 5 minus j2, 5 minus 2j. ठीक है, तो आपकी लाइन की भी इम्पीडेंस दी हुई है इस क्वेश्चन में. You have been asked to find out the average power, the reactive power, as well as the complex power of this at the source as well as at the load end. Fine. So it is actually sufficient for us to consider only one phase of a system, and from one phase we can actually calculate the power in all the three phases as well as the total power, because this is a perfectly balanced system. So we have VP, that's actually voltage in one phase is 110 angle 0 degree volts, and IP we need to calculate. So VP is any voltage here. Let me take VP is this voltage, and we need to calculate this IP. So in order to calculate the voltage, in this case, this is a star-star connection, so phase current and line current will be same. So we want to find out what is the value of IP. IP will simply be equal to 110 angle 0 degrees divided by the total impedance now, that is 10 plus 8j plus 5 minus 2j, that is this impedance and this impedance, they are in series, so you can simply add them up. Total impedance will be 10 plus 8j plus 5 minus 2j, so IP will be simply 5 divided by this total impedance, and that will be equal to this will be equal to 6.8 angle minus 21.8 degrees. So this is our phase current, or you can say the line current in this case, since in the star-star connection, line current and phase current, they are same. So our phase voltage here is VP equal to 110 angle 0, and our line phase current is simply this phase voltage divided by the total impedance, that is the impedance of the transmission line as well as the impedance of the load, that is 10 plus 8j plus 5 minus 2j. तो ये हमारा 6.8 एंगल minus 21.8 degrees आ गया. Now these are phasor quantities, these are not sinusoidal, these are not time, we are not representing them in terms of their sine equivalent, sinusoidal equivalent. So you already know that if you have been given a phasor equivalent uh, from the single phase source, we know this, that it will be equal to VP thrice VP IP conjugate. Fine. Apparent power, apparent power will be equal to thrice VP into IP conjugate. So this is equal to 3 into 110 angle 0 degrees into IP, that is 6.8 angle 21.8 degrees. 21.8 degrees because we are taking the conjugate, will not be, so ये minus sign जो था minus 21.8, it becomes equal to plus 21.8 after taking its conjugate. So this is equal to 2247 20 angle 21.8 degrees. So this is the power uh, that is produced by the source. Fine. This is the apparent power that is produced by the source. We have to find out. We have to find out these things. We have to find out the real power. We have to find out the reactive power as well as the apparent power, or you can say the complex power. So S is equal to 3 Vp Ip conjugate. If we are representing Vp and Ip in their phasor forms, so we have to take the conjugate of Ip. If we are representing them in terms of the sinusoidal quantities, so it is simply 3 Vp into Ip. तो ये तो हो गया आपका apparent power. Now real power. Real power from here will be equal to what? It will be simply S cos theta, where S is 2247 into cos of this angle, that is 21.8 degrees. So ये हो गया आपका 2247 cos 2086.3 watts. This was volt ampere. This is your real power. Real power is represented by P, and your reactive power is S sine theta, that is 2247 into sine of 21.8 degrees, that is 834.46 VARs. Now this is the power that is produced by the source. This is not the power that is being absorbed by the load. We have to also calculate power. We have to calculate real power, reactive power, as well as apparent power that is absorbed by the load. Fine. Now we already know what is the load, that is 10 plus 8J. So we can write the power absorbed by the load. If we talk about power absorbed by a load in one phase it will simply be the current that is flowing in this system, that is IP in IP square multiplied by the impedance of the system, that is ZP. Now total power in all the three phases will be thrice of that. So this will be S will be equal to IP square इसका magnitude into load, that is ZL. This is per phase. Now in all the three phases it will be simply multiplied by 3. So 3 into IP magnitude of IP here is 6.8 square into ZL. ZL is 10 plus 8J. So this is equal to 3 into 6.8 square into 10 plus 8J. This is 1776.4 angle 38.65 degrees volt ampere. This is the power, that this is apparent power that is absorbed by the load. The real power that will be absorbed by the load will be S cos theta, that is 1776.4 into cos of 38.65 degrees. That is 1387.32 watts, and Q will be equal to S sine theta, that is 1776.4 sine of 38.65 degrees, 1 1109.47 VARs. Uh, so this was our circuit, a three-phase circuit, a star-star connected system, and we had the phase voltage given to us. We knew the transmission line impedances, we knew the load impedances. So first of all, what we have to do is we have to calculate the phase current. We calculated IP by taking the transmission line impedance and the load impedance in series. ठीक है, अगर ये load is connected in a star fashion, so simply these two impedances, they are in series. It is you can simply add them up. It's easy to solve. Now if they were in delta, and then you could not actually have simply added the two impedances. So जहाँ पे फिर आपको डेल्टा टू स्टार कन्वर्जन पहले करना था, फिर आपको इम्पीडेंस सीरीज में लेनी थी. So once you have IP, once you have VP, so the power that is generated by the load, that is generated by the source, is be given by 3 VP IP conjugate. So we have this. This is our apparent power. This is our complex power rather. इसमें से apparent power का अगर magnitude हमें खाली देखना है तो that is only 2247 VA. And our real power is 2086.3 watts, and our Q is 834.46 VAR. Now the power that is being absorbed by the load, apparent power will be given by the complex power, actually is given by this particular term, out of which the apparent power is simply 1776.4. The magnitude of apparent power is these many VAs, and then you can calculate real power and reactive power by as cos theta and as sin theta formula. These were the total powers in all the three phases. If you were being asked to find out power in any particular phase, you have to simply divide any of these by 3. You will find out the power, real power, reactive power, and the apparent power, either on the source side or on the load side per phase. We'll be doing some more numericals on this. We'll be doing that in tomorrow, and with that, we actually covered